So in our last video, last two videos, we talked about section 3.5's topic of rational functions and their graphs. We looked at finding the domain of a rational function. Then we talked about when rational functions have holes in their graphs. And I showed you these two graphs. I want to make them just a little bit bigger for the purpose of pointing out that g of x is 1 over x minus 4 and has these two branches. H of x is x plus 6 over the product x plus 6 times x minus 4, and technically actually has three branches because there is a disconnected area here where x is equal to negative 6. Notice there's a hole in the graph of h at negative 6. If I divide out this common factor x plus 6, g and h are equal. But remember, I can never divide by 0. So they're only equal if x is not negative 6, because that's the value that makes x plus 6 0. So we talked about that last time. Now we want to talk about vertical asymptotes. And so let's start by defining a vertical asymptote. That's a vertical line. Remember, vertical lines have the equations of the form x equal to some number. Here we're calling that number a. So this vertical line, x equal to a, is a vertical asymptote of the graph of a function f if f of x increases without bound so in other words, this is my vertical asymptote if f of x increases without bound as x approaches a. So notice that's what's happening here. The y values, as this function gets closer and closer to a, so here's a, here's the vertical line x equal to a. As the function gets closer and closer to a, the y values get larger and larger and larger. So I have a vertical asymptote if, as the function approaches this line, here the function's approaching the line from the right, here the function's approaching the line from the left. If the function approaches a vertical line and the values of y, as x gets closer and closer to a, either from the right or from the left, and the y values get larger and larger and larger, we say they increase without bound, then x equal a is a vertical asymptote. Or if f of x decreases without bound as x approaches a. So notice here, as my x values get closer and closer to the x value of a, the y's become more and more negative. Here, as my x values get closer and closer to a coming in from the left, the y's also get very, very negative. And so another way to say what I'm seeing in this picture, as x goes to a from the right, so notice we use a plus sign as a superscript or exponent. So as x goes to a from the right, that's how you would read this, f of x goes to negative infinity. Here in this picture, as x goes to a from the left, f of x also goes to negative infinity. Similarly here, over in the picture of the function increasing without bound, as x goes to a from the right, f of x goes to infinity. As x goes to a from the left, f of x goes to infinity. So increasing without bound means your function values are going to infinity. Decreasing without bound means your function values are going to negative infinity. And you can be approaching your a value either from the right or from the left. From the right or from the left. The function can either be increasing without bound. Another way of saying that is that f of x is going to infinity. Or it can be decreasing without bound. Another way to say that is to say that f of x is going to negative infinity. So this is the definition of a vertical asymptote. Locating vertical asymptotes involves recognizing a certain form of the function, the rational function. If f of x equals p of x over q of x is a rational function in which p of x and q of x have no common factors and a is a zero of q of x, the denominator, remember q of x was our denominator, then x equal a is a vertical asymptote of the graph of f. Another way to say that I think helps with the understanding of what's actually being said here is to say if f of a takes on the form of a non-zero number over 0, then x equal a is a vertical asymptote of f of x. When you say this way, then you're dealing with this fact about that the numerator and denominator have no common factors. And a is a zero of q of x. So if you substitute a for x in your function and you get a non-zero number over 0, then the result is that your vertical line x equal a is actually the vertical asymptote of the function. Let's look at this example where f of x equals x over x plus 4. Now notice that f of negative 4 equals negative 4 over negative 4 plus 4. So that gives me negative 4 over 0. Now the important thing to notice about this is that this is actually undefined. Remember, I can never divide by 0. So what this allows me to conclude is that x equal negative 4 is a vertical asymptote of this function f of x.